I hope everybody received the results of the evaluation. And in this case, I didn't have the time to scan all this work. That's why I tried to summarize your results according to the rubrics, and I share with you the rubrics so you have the detail how was evaluated. Results are really low. The mean was 39. Deviation was 12, almost 13. So it's about 30% of the mean value, the average. That means that you are very spread. The maximum was 62, the minimum was 18, and then according to the results by question, in the first question was about programming, Python programming, you got 61%. So just in the average, what you're supposed to have. In question 2, you got 51%, just a little bit below 60. And then in question 3 and 4, what very low. In question 3, you got 22%. And in question 4, 17. In question 4, there were many people who, well, not many, but some of the students, not one, several students who, I don't know, they try to analyze the stress, for example, as it were a bar. They said the stress is equal to P over A. That's a bar, but you review the problem statement and it mentions the word beam or bending. I think it was 4 times. Let me ask you something. For example, Miss Vera, what's the difference between a bar and a beam? Miss Vera, can you hear me? Miss Vera, are you there? No, she left. Mr. Iñiguez, are you there? Mr. Iñiguez? Mr. Iñiguez, are you there?
Doctor. Yes.
What's the difference between a bar and a beam? Is the same or is different? Go on.
In the beginning, I pay attention in force and moment. In the bar, only force.
In what direction? In the case, because you said
a line. In bar is a line, and the beam is in the
lateral, right, perpendicular direction. So that's a huge difference. So when you calculate normal stress in the case of a beam, you consider bending moment. The bending moment produces a distribution, which is a linear variation starting from the neutral axis. In the case of the bar, you simply say it's just uniform over the whole section. So normal stress is just P over A. If P is positive, that means that sigma is positive and the bar is in tension. The opposite bar is in compression. Okay. Any other comment about the evaluation? Any other comment about the evaluation?
Carrillo, the fourth topic in the quiz is your resolution. This is only way solution, or we have the other method of solution?
The question is clear. You need to determine the Young modules.
Yes.
So that's the objective of that problem. The bending moment was an intermediate result. You could solve the 4th order differential equation for that. It was a waste of time,
Yes.
because you don't need V. You need the second derivative because you are interested in the bending moment.
Mm.
After solving for V, you can go back, evaluate the second derivative. And then
Right.
you can go on, calculate the stress. And with the stress, you can calculate the Young modulus.
In my solution, I developed, for example, the begin in the equation de equilibrio de beam. I integrate the four location, find the deflection.
Did you find the bending moment?
No, is yes.
You could start solving any equation that you want. Did you solve
Yes,
for
yes.
the bending moment? Did you calculate the bending moment?
The question, yes.
No, not the equation. I see. I know the equation by memory.
Yeah, yeah.
That's. I mean, you write the differential equation. What's the thing about that? I can write it. Anybody can write it. The thing is, did you solve it?
I have a solution.
This
Okay.
is a simply supported case, Mr. Carrillo.
Yes.
It's a simply supported case. Think about it. The complexity of this problem. It's nothing. If you cannot solve this problem, what do you want from me? Determinate beam problem. If you cannot solve a beam which is statically determinate, we're in trouble.
Okay. Thank you, doctor.
No problem. So people, you better start studying. You better start studying.
Other question, doctor. Sorry. The three topic in the quiz is important. Determine the number correct the joints or no?
Yeah, so what you need to do is specify the number of the joints. Yes. Why? Because when you use those numbers to specify the beam elements, you need to say which one is the first and which one is the second.
Okay.
Because when you calculate the local displacements, you need the local displacements to calculate the strain. And finally, with the strain, stress, and with the stress, internal force, axial force. So it's very important that you specify correctly not the numbering of the joints. What you have to be very careful is with the numbering of the joints in one element. See, I said this is joint 3 and this is joint 11. So this element goes from 3 to 11. That means that this is the local axis. But you could also define, we're going to do that today. You could define that from the 11 to the 3. But in that case, the x-axis would be this. And of course, the theta is different. We did an exercise on that in class.
This is my error. For example,
every time we did an example, I started with the connectivity table. I said, okay, these are the joints, these are the elements, and then I put it a little table. I said, element 1 goes from joint 1 to joint 2, whatever. The other, each one of the elements. So with that, I draw a local axis, so I try to check. Okay, I see the position of the local reference system with respect to the global. And then you can define theta and proceed.
Thank you, doctor.
No problem. Okay. Something that, for example, it's something that you should have. You should, see, I want, at a certain time, I thought about asking you, but it is something that you should do by your own initiative is that when you take a quiz, it's a good idea that if you consider that you did not well in that quiz, you should try to solve it after class to learn. The thing is not to have 60 to pass this class. The thing is to learn. And when you make a mistake, it's a very good idea to try to determine what was your error. Once you identify error, I'm very sure that in the next occasion, you're not going to commit that error. Maybe another one, but not that one, this one. But that's your initiative. Did anybody, would you please raise your hand, those who try to solve the quiz after that? Did anybody did that? Would you please raise your hand if you try to solve it? No. Anyway, see, I thought about asking you to do it, but I prefer to let you do it by your own initiative. But you see, that means that you're not in here with your 100% senses. You're thinking more in Barcelona than Emelec instead of finite elements. Okay, people. We started last class with an example using two beams, okay? But these beams that we're using, they include both effects, not only bending, but also in-plane load, okay, axial forces. So that's an element that supports bending and axial force. You could also imagine or develop another element which can support not only bending, in-plane loading, but also you could include torsion. Or you could include, for example, not only bending in one plane, but also in the other plane. So in that case, you would need inertia, see inertia for this with respect to this axis, inertia with respect to that axis, and inertia, to polar inertia to calculate the torsion. So that would be a more complex element. And that's what you will have in when you analyze this type of problems using ANSYS, for example, okay? It's a more complex element. So in this case, we're considering only an element that includes two effects, okay? Aligned loads and lateral load. We're going to review that quickly, and then I'm going to try to present that. That's in the PowerPoint that I shared with you. The same problem with a different definition of one of the elements. And of course, the answer has to be the same. At the end, I'm going to make a couple of comments about the assignment. Okay, finally, I was able to find in my records, I didn't remember, but I have this publication, SNAME publication. I have it scanned. I don't know, I asked somebody to scan it. So I put it in the Teams platform. Hopefully you were able to find it. Unfortunately, I don't know what happened last night or yesterday afternoon, yesterday night, but I couldn't load it in the Aula Virtual. I don't know what was the problem. I have to ask Ricardo. But I was trying to put in the same assignment to load this file, but I couldn't. That's why I had to put it in the Teams. So we're going to comment on that at the end of the session. Okay, let's see if we can do something about this example beams. Okay, let's review this first. People, can you see my projection? My
Yes.
projection? Okay, thank you. So this is just the beginning. I'm not going to go over this. Here. Okay. We have one global reference system. Usually we put the X in the horizontal direction. That's not necessarily so, but that's very common. And then in red, we have a local reference system. If we have a vector D, this is a vector, if you express in the black or in the red reference system, they should point in the same direction because it's the same vector. Okay, this is something that we did in chapter 1 to transform a vector, that's the two coordinates, from the global to the local reference system. Okay, that's something that we have to remember. Cosine sine and sine cosine. And then the rotation, since we are working in the plane, okay, the rotation points normal to the plane of the paper. That means that the rotation in both reference systems, see here, this rotation is the same because it points in the Z direction. See, the Z direction points perpendicular to the plane, both for the global or for the local reference system. So it's the same. That's what we're saying here. So if we have these 3 degrees of freedom for joint 1 and this other for joint 2, okay? And we are going to transform that from the global to the local reference system. This is the matrix that we need. So this thing here, transform the vector in the XY plane, and this one transform this into that. There is somebody in the waiting room.
It's already in.
Okay. Similarly, the same matrix for the second the second joint. So this is a vector, and this is just another vector which is perpendicular to the plane. So this is the way we put it in a summarized way. The vectors in the local is equal to the vectors in the global times this T matrix. In this case, you see that this is a 6 by 6. You can imagine that as we go on, the complexity of this matrix gets increased. We get more and more degrees of freedom. In this case, you can see that we have 3 degrees of freedom for every joint. At the end, in the general case, we're going to have 6 degrees of freedom. We're going to have 3 translations and 3 rotations, okay, for every joint. Okay, so what we did was in chapter 1, we considered bars, okay? And the bars are elements which support only aligned forces, okay? So that's why the first one here produces the external force in joint 1. And the second, the fourth line produces the external force in the X direction in joint 2. All the others are zeros. EA over L. We recognize EA. That's the stiffness in the axial direction. In this chapter, we are considering lateral loads, okay? So in this case, instead of EA, we have EI sub C. This is the bending stiffness of the beam, okay? In this case, this line here, the second, produces the external force in the first joint, but this external force points in the vertical direction. The third line produces the moment, external moment, in the first joint. Similarly for the second joint. So since we're working with the linear problems, what we can do is we can consider both effects. Okay, so in this case now, we have an element which can support in-plane force and lateral force. So we can support both effects, okay? So this is the equation that we have to set up in order to establish the equilibrium of one element, okay? This element supports aligned forces and also lateral forces there, okay? So we have all of these, all of that in here, and all of that. So please, this is something that I noticed in your exam. You spent a lot of time writing every element in this matrix. And when you, okay, we're going to do this, and you repeated all of these values in the next page. Just repeating. That's good for primary school. This is university. Do you need to write all of this? What elements of this matrix do you need? And that's only what you care. The others, you can put just a letter. You don't need them. But it's your time, not mine. This is a summary. Please, here we have both effects. We have this and we have that. So in here, I have EA-L and also EI sub C. Okay, all of this is in here. So since this is a vector, we transform it from the globe to the local to the global. This is another vector. We use the same transformation to get displacement in the local, in the global. So this is, you see that it is on the left of this product. So when you move it to the other side of the equation, it has to be placed in the same position, to the left of a vector. This product here is a vector. So you have to put this in here with the inverse. This transformation has this property, very special property, which is that the transpose is equal to the inverse, okay? Hope maybe you remember from your high school years that calculating an inverse is a very long process. So it's much simpler to calculate the transpose, okay? So here, how many elements do we have in the T matrix? Somebody, how many? What's the size of this matrix, this T transpose? Anybody? This T transpose, please, anybody? No, it's a 6x6, okay? Similarly, the K is also 6x6, and the T again is 6x6. So this produces a 6x6 matrix, okay? This is the stiffness matrix, okay, for an element which supports both in-plane and also lateral load, okay? I'm trying to write something here, but it's, okay? So this means that this is for one element, okay? This matrix here, it's a 6x6. So this is a 6x6. And you don't need to remember that matrix. Somebody in the last problem had learned, putting in his memory, the full matrix, this matrix. And it was a waste. I understand this is not a race for memory. So you don't need to put all of this in your memory. I'm going to give it to you in an evaluation, okay? But I can ask you, for example, the result of this is going to be one element. And I can ask you, how did you get it? If I give you this, I give you that, how did you get that element? And you should be able to remember that this is the equilibrium This is the same equilibrium, but expressed in a different reference system. And from there, you get this product, which can be identified as the stiffness matrix of the element in the global reference system. Okay. Then we have to apply boundary conditions. Okay. So you have to have no supports. Solve, remember, we solve in two subsystems. And after we solve the first subsystem, you know all the displacement in the discretization. Then in the second part, the second subsystem gives you the reactions. Okay. Then for every element, okay, you calculate the displacement in the local reference system. And then for that, you calculate the T matrix. Okay. And this T matrix depends on the definition of every element, because the definition of every element determines what's the theta value for that element. And after you calculate the displacement in the local reference system, you can calculate strains. When the strains, you calculate stresses using Hooke's law. And if you need, you can calculate internal forces. And finally, you can evaluate, analyze results. Okay, a couple of things before we go to the example from today is in November 4th. Okay, when we set up yes.
You're not writing.
See the right.
You what?
The slide is empty.
You cannot see.
No.
And it's not full screen.
Okay, let me try to correct that. Let me try to correct that. Okay. Can you see my PowerPoint now?
Now, yes.
Okay. Let's see this. Show this interview. I forgot to do this. Okay. Can you see my screen?
Yes.
Okay. Okay. What we're saying is that in the global equilibrium, oh man. Okay. In the global equilibrium, we have something like this, a very large matrix. Okay. And then we have the displacement. Okay, let's suppose this is D1X, D1Y, let's say Phi1Z. And the last one is going to be Phi NZ. Okay, what? Now, on the right-hand side, we have this is F1X, F1Y. The last one is going to be M and Z. Remember, these are external forces. Okay? For example, in the case of the evaluation, we have a bar like this. We have a cable here. And we have a force here. Okay, so let's suppose I call this joint 1, this joint 2, this joint 3. Okay, The global reference system, we put it like this, X, Y. That's it. Now, if you want to solve this, this system of equation, you have to have, let's suppose this is n by n. Okay, this matrix. This is a big K. This is the order of this matrix, capital N by capital N. Now, if you want to solve this, you have to have n unknowns. If you have less or more unknowns, you can have problems. For example, let's suppose that you have less than n unknowns. In that case, you have to solve for the solution, but you have to include it in a special algorithm. Okay, because you have too many equations. In the contrary, you have less equations than unknowns. Then you have to find something extra. If you have exactly n unknowns, n equations, yeah, the solution is standard. Okay, and this is what we're talking about. Now here, in this case, for example, f1x. What's the value of f1x? What's the value of f1x? Anybody? People?
The reaction.
What's the value? Do you know the value?
No.
So it's unknown. I'm sorry, in this case, I shouldn't include fees because this was the problem from chapter 2. But anyway, in general. So this is unknown. And you go on, and at the end, you have to have this number of unknowns equal to n. That's the number of equations. This is not 0. So when you have here, for example, you said this is equal to 0, this is unknown. So this is something that we describe in class. In every equation, in this case, you do not know f1x. Okay, in the second equation, okay, you do not know f1y, etc. So in every equation, you either know this or know that. So at the end, you can check that this is the number of unknowns. So in a point, when you have this support, in that point, f1x, as somebody said, is the reaction. This is something that we do not know. It's not equal to 0. Okay? It may be 0, but in general, it's something that we do not know. So we have to include it as an unknown. Okay, so that's something that many people write that f1x was 0, for example, and that's incorrect. That's something that we do not know. It's an unknown. The thing is that for the problem, you did not need to calculate the reaction. See, because with the displacements was enough. Okay, that's something that I want to emphasize. There's something else that I forgot. Let me see if I remember. Okay, if I remember, I'll comment on that. Okay, so okay, now let's go to the example. Okay, can you see the PowerPoint with the examples, people?
It's charging. Now.
Okay, thanks. Let me try to. Okay, this is the example of the aligned. Some people for the aligned case, problem 2, try to use the full matrix for the bars in the plane, and you waste your time. But immediately you see that that's somebody who did not do the homework. That's the message for me. Okay, so this is the problem. Now, in this case, okay, if you push this downwards and move this to the right, okay, for example, because of this action, this vertical beam will bend. Okay, also since this is clamped, because of this force and this force, this also will bend. But because of this compression, this element will be in compression. And these points, these two forces also will produce an axial force on this element. So in this case, we need to consider both effects, okay? Bending and also in plane force. So that's what we need, this element, which is beam and bar combined. Okay? And then we go. This is the first thing that we do, okay? So we have to define how many elements do we need. In this case, we use 2 elements. And the first one goes from 1 to 2. So immediately, if this is a local reference system, you see that theta, it's about 45 degrees. It's something that we have. So this is the local reference system for the first element. That's that. But then the second, we go from 2 to 3. So this for the second, that's a local reference system. That's X local for the second. And this is your Y local for the second. And this is your theta, which is negative. This is theta for the first one. So that's what we need to do. Okay?
Doctor,
Yeah.
question. The element formed by the joint 1 and joint 3, what this is not element to consider?
No, this is nothing. It's nothing because it's just foundation. This is not an element. This is foundation.
Okay, thank you.
That's all what you need. In the case of the evaluation, okay?
Doctor, I have a similar question. In the joint 2, what are we considering? It is a clamped between the 2 elements.
See, when I write something like this, okay, and I put a dot here, that's a pin. This is a pin. And the pin, remember, this is something you have been working since solid mechanics, does not transmit what? Moment. See, you have 2 things like this, and you put a pin like this, okay? The 2 elements can rotate freely, one with respect to the other. Okay?
Yeah, but there is no pin, so that is the question.
Exactly. In this case, there is no pin, so that's like this, the same, right? The same corner, like this. So this end cannot rotate freely with respect to this one. So if this one here rotates, let's suppose this is the original direction. Let's suppose that this point rotates to this point. The other one, okay, they have to rotate in the same direction. So this has to come to this. But if this rotates and forces this one to take this angle, forces, you have to transmit what in order to make this to rotate the same amount? What do you have to transmit? You have to transmit moment. So in this case, oh Jesus, the pin is gone. Then, oh gosh. Let me go back to the, here. We need a pin here. There. If you analyze the equilibrium of this element, okay, between them, you have to consider only forces. When you analyze this equilibrium, in here, you have to consider bending moment or moment in general. I don't know if I answered the question of the person. Did I answer? Okay. Okay, now let's see this. So this is something that has to be very clear. So in this case, we have to consider both effects in plane, and also we have to consider bending, okay? So when you start seeing that this is clamped, very likely that you have to consider bending, because this means that there is no rotation. And to avoid rotation, you have to develop a moment. A moment means beam. Okay, so this is all the information relevant to element 1. And this is well, everything is important, but one of the most important is this one. Is the fact that you need this angle, 45 degrees. So it is this angle here, this is 45, as you can see here. Then for the element 2, that's what is very important in this case. Okay, so we are, I don't know where is oh, here it is. It's minus 90. So this is something that we recognize from here to there. This is negative. This is negative. Okay, or we can say that this angle is from here up to here, and that's 270. But you evaluate the sine or cosine of minus 90 and compare it with the sine of cosine of 270 is the same. So you can put here, if you want, theta and you get exactly the same results. Okay? And then we go. Remember, this in this case, this is a 6x6 matrix. So we have up to here and up to here. Okay? So the first one, you see here, the first one here. So this is F1. Let's put it as a vector, okay? That means that F in the X, Y direction, and also the moment in the first joint. And this 3 corresponds to F2 vector. That means that the two components, X, Y direction, and also the moment. And they are the result of multiplying these numbers times the displacement of the first and the second joint. Similarly for the second element, okay? So here is something that we review it. Where are you? What is the pin? Where is the pin? Here. So this is the first element. This is the second element. And immediately you see that this area in blue, it's the common area, and that corresponds to joint 2, which is the common joint in both, for both elements. Again, we see here that, where are we? Jesus Christ. We see here, D1X is 0, D1Y is 0, phi is unknown, D2x is unknown. D2y phi is unknown. This is 0. I'm sorry, this is clamped, so this is also 0. This is 0, and this is 0. Now, F1x is unknown. F1y, M1z are unknown. F2x, it's 49,000. F2, it's minus 980. M2z is 0. This is it. And you see that we have 3 unknowns here. And here we have 6 unknowns, total of 9. So 9 equations, 9 unknowns, and we can proceed to try to solve it in a unique way. So the results that we obtain are unique. Okay, let's take a break here, and when we continue, we can complete this example, and then we can proceed to analyze the same example, but with the in a different connectivity. So instead of having the element from 2 to 3, we're going to define the second element from 3 to 2. In that case, the theta would be different, but the result has to be the same. Okay, so let's take a break here.